There are few sensory experiences as universally recognizable as the sharp crack, the brief hiss, and the sudden spray of carbonation from a cold beverage. In the next 60 seconds, while you watch this very scene, over 1 million of these will be opened by someone, somewhere around the world. It costs merely pennies to manufacture, yet it seamlessly holds back 3 times the internal pressure of a standard car tire. What sits quietly inside your refrigerator is the result of thousands of micro-adjustments and mechanical forces that push the boundaries of modern manufacturing. To understand this physical paradox, we examine its construction. Here, the metal wall of a standard can is compared to a human hair. The metal is visibly thinner, yet this fragile barrier must contain the explosive outward force of internal carbonation without structural failure. Achieving this exact physical balance requires a manufacturing process that is violently fast and microscopically precise. Creating billions of these flawless vessels every single year requires a system designed to survive the laws of probability. That journey begins far from your kitchen, inside sprawling, windowless industrial facilities where raw material is processed. 10-ton spools of metal are unwound into continuous ribbons, stretching nearly 3 miles long. This is a highly malleable, proprietary aluminum alloy. The metallurgical requirements here are ruthless. If the exact temperature of the alloy is off that even a microscopic fraction of a percent, the rapid tension will tear the metal, halting a multi-million-dollar production line instantly. The aluminum ribbon is fed first into the cupping press. Operating with a deafening speed that mimics heavy machine gun fire, a heavy steel die punches out thousands of shallow metal cups every minute. This initial brute force is impressive, but it only creates a shallow, useless blank. The true engineering trial is yet to come. The shallow cups are forcefully thrust into the next stage, the wall ironer machinery. As this schematic illustrates, a high-speed steel ram punches the cup downward through increasingly narrow tungsten carbide rings. With every pass, the metal is stretched and ironed out until it forms a tall cylinder. This extreme stretching generates immense friction. Copious amounts of specialized chemical coolant must flush over the system continuously to prevent the thin aluminum from melting under the heat. If you look closely at the base of the resulting cylinder, you will see a specific structural feature. The metal is shaped into a dome. That specific domed arch distributes the intense pressure of the carbonation outward, ensuring the incredibly thin metal base does not bulge or explode in transit. Sealing the top of the cylinder presents a different challenge. The lid must be made of a thicker, heavier alloy to hold the opening tab. To minimize the amount of heavy material needed, the factory employs a process called necking. Through a sequence of rapid spinning stages, the top diameter of the can is squeezed and tapered inward by just a few millimeters. Shrinking that small diameter across billions of units saves the industry thousands of tons of aluminum every year. Maintaining this level of precision requires a constant human element. As the heavy steel machines run, they generate heat and expand. Mechanics navigate the floor dynamically adjusting the machine clearances by fractions of a millimeter to compensate for that thermal expansion. The entire gauntlet rests on a fragile equilibrium between violent mechanical force and hypersensitive human calibration. The surviving unpainted cans reach the final quality control line, moving at a velocity of 2,000 units per minute. Inside a dark chamber, each unit is blasted with intense light, while hypersensitive optical sensors scan the interior, searching for microscopic pinholes thinner than a speck of dust. If even a single stray photon of light passes through a microscopic fracture, an automated air jet instantly fires, blasting the defective can off the line in exactly 3 milliseconds. It is a system of zero-tolerance judgment. Only mathematically perfect vessels survive to see the end of the line. Stripped of the chaos, the surviving cans arrive on the logistics floor, where silent, automated robot forklifts stack them into monolithic cubes towering 20 feet into the rafters. The physical volume is difficult to comprehend. A single facility easily produces over 5 million cans in a 24-hour shift. Laid end to end, one day's output would stretch continuously from New York to London. To sustain that unrelenting pace, facilities are now deploying predictive AI algorithms that listen to the high-frequency ultrasonic vibrations of the factory motors. By analyzing that auditory telemetry in real time, the algorithms can pinpoint when machinery will break down or material will fail, long before a human mechanic could detect it. In this environment, the hardware functions as a self-diagnosing network, identifying its own weaknesses before they ever lead to a failure on the floor. Sustaining this volume is possible because of the material's unique physical properties. Aluminum is infinitely recyclable, retaining its malleability no matter how many times it is reprocessed. As this flowchart tracks, the moment a can goes into a recycling bin, it enters a remarkably fast closed-loop cycle. It is melted, reformed, filled, and placed back onto a supermarket shelf in exactly 60 days. This process drastically slashes carbon emissions, turning yesterday's waste directly back to tomorrow's high-performance vessel. Which brings the industrial journey right back to your personal experience. The next time you hear that satisfying crack, take a second look. You are holding a vessel that survived a mechanical gauntlet, shaped by forces and tolerances that most industries never attempt.